So a few years ago, I was lucky enough to get a piece of property in the mountains with a nice little stream. And I definitely would say I was like micro hydro curious at the time. So I did a little bit of research and was like, oh yeah, totally. With no experience whatsoever, I was like, yeah, I could do that. And pretty much cannonballed into the deep end of the world of micro hydro. Because how do you look at that and not think, wow, that is sexy. I want to try that. And through the learning process, there have definitely been days where you're just like, call the power company, tell them to put the posts in. Like, I am over this. Nothing is working. But then there's the days when everything is going right and there's no better feeling than walking into your house, turning on your lights, and just thinking, I am man. Man make power. And I spent the past 4 or 5 years learning an absolute ton. And I would say I definitely fell victim at the beginning to chasing power. How much power can I make, right? It's a really important number. But as I've learned more, I would rather have a system that doesn't wake me up at 1 o'clock in the morning going, somebody's freewheeling. We all have enough chaos in our lives. If there's going to be anything that's boring, stable, reliable, it's okay if that's my hydro system. Because when the power goes down, I live off grid. So sometimes it's days, sometimes it's months, but I'm out of power. So with this video, I'm going to go through each component of the microhydro system, how they work together, and how you can set them up to increase the overall efficiency of how your system works, not necessarily how much power it can make. Because if you just set it up and let the electronics do whatever they want, they're gonna ruin your day. Ask me how I know. So right now, the water coming out of that nozzle is traveling at over 100 miles an hour, and it's spinning a 5.5-inch wheel. So you would expect that wheel to be spinning really fast, right? Well, that would be really bad for it. So to prevent that from happening, you need an opposing force to keep the wheel from spinning too fast. And that opposing force that pulls against the water pushing is basically your power. And what controls the pulling force on that to make the power is the most important relationship in the whole show. And it lives right in here. In this unit, there's something called an MPPT, or maximum power point tracker. So the best analogy I've been able to come up with between the relationship of the MPPT and the microhydro is if you imagine you're riding a bike. When you first start pedaling, it's quite hard to get momentum. But once you do, the pedaling actually becomes kind of easy for a little bit. But if you can't stop pedaling, you're just going to go faster and faster and faster to the point where it's no longer efficient because you're pedaling so fast. But there's this kind of band in between where it's too hard and too easy. But if you were to apply a little bit of brake pressure while you were pedaling in that zone, that would allow you to stay in that zone. Turbine's pedaling, the MPPT is braking. If it brakes too hard, it'll bog the turbine down and it'll be too hard to pedal. If it doesn't brake enough, the turbine ends up spinning too fast and it's inefficient because it's spinning so fast. So it's called the maximum power point tracker because what it does is it tracks that efficiency band. And all it's trying to do is figure out, where can I put the most brake where it's still the easiest for the turbine? And that balance point will create the most power. And just to be clear, the MPPT gremlins, they only care about this number right here, the total watts that are coming in. When we see these numbers change, all it's doing is asking, am I making more power with this much brake? Am I making more power with this much brake? What about this much brake? Because those little gremlins, they'll jump on your bike, put it in low gear and pedal downhill as fast as they can just to see if they can make more power. So that's the MPPT's job. Find as much power as it possibly can and use that to charge the batteries. So what happens when the batteries fill up? Well, this is the biggest difference between microhydro and solar. Solar is kind of polite. If the batteries are full, they don't need any more power, solar's like, no worries, I'll just hang out. It's cool. They don't get damaged just hanging out in the sun. Whereas water is kind of a dick. It doesn't really care if your batteries are full, if your inverter is super stressed. It doesn't really care if you're asleep or what time it is. The water never stops. So if there's nothing loading the generator of the turbine, the water just gives her, right? It'll spin that turbine as fast as it possibly can. It's called freewheeling your turbine, which is very bad. And if your turbine starts freewheeling, not only is it really bad for the machine itself, because the bearings aren't designed to spin that fast, the RPMs and the voltage are directly related. The faster it spins, the higher the voltage. So you're also risking damaging some really expensive electronics downstream. If your turbine starts to freewheel, it's called voltage open circuit. It's the highest voltage your turbine can spit out. And if your system isn't designed to handle the open circuit voltage, you're risking damaging all those electronics down the line. Okay, so now that we understand their relationship and how they work together, it gets really, really fun because we can watch them interact in real time and understand what's happening. So as I turn the water on and the turbine starts to spin, you'll hear the RPMs on the turbine change. And we now know that change in RPM is the MPPT putting different brake pressures on the turbine and asking, are you making more power here? Are you making more power here? Are you making more power here? So I'm going to stop talking and we'll listen to the turbine. Cool! So could you catch those little steps in the changes in RPM? I just think that is so cool. But it's also a little misleading because I'm sure now it's really easy to think, well, if the MPPT is braking the turbine, it must be controlling the RPM, right? We heard it. Wrong. But I did say that the RPM and the voltage is directly related. So maybe it's controlling the voltage. Maybe the MPPT is using this voltage, and when it changes the voltage, we're hearing the result of that as a change in RPM down in the bottom of the powerhouse. And we see the power changes as the voltage changes. So maybe the MPPT controls the voltage. Unfortunately, that is also incorrect. It gets a little complicated here, so I'm not going to get into the weeds. But basically what's happening is the MPPT is pulling current, which we measure in amps, out of the turbine. Because watts, volts, and amps are all related, what we see as volts and power and volts and RPM, we see all of those change. That's a result of the MPPT pulling current from the generator in the turbine. If you're not confused by now, I'm gonna keep trying. So let's take a look at that same relationship, the MPPT to the turbine relationship, but from this side of the wire. So instead of seeing the RPMs change, now we're gonna watch the voltages change. Remember, the voltage and the RPMs are directly related. And if you watch MPPT TV for long enough, you'll see where the efficiency band that it likes to scan in. So mine is roughly 180 to 160 volts. That's where the MPPT likes to search. That's where it gets the most power. And the reason why it's important to know what that efficiency band is because that's how these two talk. The MPPT and the diversion load controller. The diversion load controller is basically a voltage sensitive relay. So it's watching the voltage on the whole system. And as long as the MPPT gremlins are charging the batteries and staying within their efficiency band, the diversion load stays out of the way. When the batteries are full, the MPPT gremlins are just gonna walk away. They don't need power to fill the batteries. Their job is done. They're going on break. And as soon as they do that, the MPPT will unload the turbine and leave it to freewheel. Because they don't care about the bearings in your turbine. And as they unload the generator, the turbine speeds up, the voltage increases, and you can set the voltage on this that's watching the voltage to divert the load on the generator to the heaters as soon as it sees that the voltage is high enough. So because the efficiency band is 160 to 180, I have this set at 197. So imagine really simply if you had a gas generator with an extension cord and you're charging the batteries with that extension cord. At some point when the batteries are full, you're unplugging it from the batteries, plugging it into the heaters, right? So you're just trying to minimize the time that that cord spends unplugged, because unplugging the cord is unloading the generator on the turbine. Okay, so we're gonna try to catch this transition in real time. So right now the MPPT is at the upper end of its happy efficiency band at 180, and the diversion load just kicked on, and now we see it jumped up to 195. So the only time the turbine was unloaded was between 180 volts and 195 volts, so just for a split second. So making oh, it just jumped up to the diversion load. That was a big jump. And the best load for that excess power to divert to is usually heat. And whether that heat is an electric hot water tank or nice, lovely, warm, lovely baseboard heaters strategically placed to keep both you and your pipes from freezing all winter, it doesn't really matter. You can use that extra power for whatever you want. And that's kind of the magic of microhydro, is not only can you use that power for whatever you want, but you almost have to use that power for whatever you want, because that power that you're using is what's keeping the generator on the turbine loaded. And remember, without the load, that's when the turbine runs away. So, as we're learning though, you can't do anything really fun without having the system completely try to self-implode. So there are a few things to keep in mind with your diversion load. And the first one, you saw me mention the hot water heater. Because the job of your diversion load is a continuous load on the generator, it is not a good idea to use anything with a switch or a timer or anything that could potentially turn the load off, like a thermostat in a hot water tank. When the water gets to a certain temperature, the thermostat turns off, the load disappears, and your turbine will freewheel. So that's why there are ways to do it. You just need to get creative with how you use those loads with timers and stuff. But a baseboard heater, that's why those are kind of the number one fail-proof diversion load, because they will burn as much power off as you send them, and they work continuously. So the second thing you want to consider when you're designing your diversion load is that it can burn off 100% of the power, the maximum power that your turbine can create. Sounds simple enough, right? Okay, so let's do an example. Say the most I could possibly make in my system is 1,000 watts. So I need to design my diversion system to be able to divert at least 1,000 watts. And I want to do it with baseboard heaters. So I go out and I buy myself a 1,000 watt baseboard heater. But these baseboard heaters usually come with a voltage rating. So this is a 240 volt heater. So if we divert our power at 240 volts, no problem, this heater can handle it. But what happens if we change that voltage? So for instance, if we were to divert 1,000 watts of power at half the voltage, at 120 volts instead of 240, this heater becomes only 25% efficient. So in order to burn 1,000 watts of power at 120 volts, you need 4 of these heaters. You need 4,000 watts of diversion power. In fact, the diversion load is so important to a micro hydro system that most of the diversion loads that I've seen are actually redundant, meaning there's a diversion load to back up the diversion load in case anything fails. Because if your diversion loads fail, you probably guessed it, your turbine will try to destroy itself. And you can see on this diversion load, you have one diversion load here and one diversion load here. And that way, my turbine is safe. Okay, so now that we're getting a better idea of all the components involved and how they all talk to each other, we're going to circle back to the beginning. And why do I prefer a system that's more emotionally regulated than just a power-hungry system? And even if that is my preference, how do you do that? How do you make a hydro system behave? And the answer is this machine right here. This is the Stream engine, and it is an absolute beast at what it's designed to do. For starters, we talk about the RPM being directly related to the voltage. But with the Stream engine, in this box here, there's 4 different ways you can wire it that will adjust the voltage when it starts to spin. So mine is adjusted in a way where it spits out the highest voltage possible. That's good for my system because I have a long run. My wire is 218 meters. That's over 700 feet. So the higher the voltage I can send, the more efficient that wire run is going to be. And the second most defining factor of the Stream engine doesn't look like much, but it's these few millimeters right here. This is the distance in between the stator, this bottom section where the coils are, and the rotor, this top section where you can see these magnets. So the distance in between the stator and the rotor create your magnetic coupling on the generator. And you can imagine the magnetic coupling on your turbine is like the stickiness of your brake pads. A strong magnetic coupling means your brakes will work really well. A weak magnetic coupling is like having old brakes, where you have to squeeze the brakes really hard before you start to slow down. So we're going to start our experiment by putting the brakes on. So by holding the rotor still and turning this big nut up here, you can see the distance is getting smaller. So I'm increasing the tackiness of the brake pads. And because there always needs to be a little bit of distance between the stator and the rotor, after you make them closer together, you always want to give it a spin with your hand to make sure that it's still spinning freely. And just so you know, all of my tests were done at about 140 psi, and I was only using 1/4 inch nozzle. Okay, so now that we have increased our magnetic coupling or put brand new brakes on our bike, let's see what RPM we are spinning at. So the MPPT has found its maximum power point around 1600 RPM. Okay, let's see, with a strong magnetic coupling at 1600 watts, we are making about 500 watts of power at 182 volts. So it looks like we've lost a little bit of power. So by increasing the magnetic coupling, by increasing the stickiness of our brake pads, we made it too easy to slow the turbine down. And we slowed it down out of the efficiency zone. So let's go decrease the magnetic coupling and see what that does to our total watts and volts. Okay, so this time we're going to increase the distance between the stator and the rotor by 1 rotation. So we are decreasing the strength of the magnetic coupling. And away we go! By decreasing the magnetic coupling, we've increased the RPMs up to 2230. Okay, so at roughly 2200 RPM, so it did go all the way up to about 176, 175, where we're getting about 650 watts. Shall we go decrease it some more and see what happens? So this time, we'll increase the magnetic coupling by a half a turn. Okay, so after that half turn, we are sitting pretty at about 2,500 or so RPM. How much power are we making at about 2,500 RPM or so? Looks like at 172 volts, we are all the way up to 730 watts. Shall we decrease it some more and see what happens? All right, let's go another half a turn. We are just over 3,300 RPM. 3,303. Okay, let's see what our power's at 3,303 RPMs. 770 at 163 volts. So we went up another 50 or so watts of power, but now you're starting to see a little bit of inefficiency because that 50 watts of extra power costs us almost 1,000 RPM. Increasing magnetic coupling, another half a turn. We are now sitting at about 3,850 RPM. Woo, she's giving her now. Okay, what's the magic number this time? Ooh, 776 at 172. But at what point is the efficiency of getting that little bit of extra power harder on the whole system than just settling for a little bit less power, but the rest of the system, specifically the RPMs of the turbine, are much happier? Okay, so I'm just gonna put the brakes back on this thing really quick. Our power is back to about 700 watts. We can see now that our maximum power point voltage is all the way down at 135. This is a bit extreme, but to the astute observer, you probably noticed the maximum power point voltage was falling through that whole experiment as the amount of power we were making was increasing. Why would the maximum power point voltage trend be important? For my system, I want that voltage as high as possible. So I want that maximum power point nice and high because I have a long run. So the higher the voltage, the more efficient. And if you remember the heater, so exactly the same physics behind it. If you send 1 kilowatt of power down a 218 meter line at 120 volts, it's about 25% as efficient as sending it at 240 volts. Now that being said, you can't control where the gremlins controlling the MPPT want to sweep to. And this is a great example. So even though the batteries are charging, I just saw the voltage down at 135. Why was it down, all the way down at 135, and now it's going all the way back up to 200? Because the gremlins are riding the bike downhill, baby. So you need to design your system so that if your MPPT sweeps all the way down to its bottom range, which we know on ours is 120 volts, that gives you the highest current, the highest amps. So you need to design your system so that when it hits the lowest voltage and in the highest current, that your system can handle. Okay, so hopefully you have a little bit of a better idea of all the different components that are involved in the microhydro system, how they all communicate together, why it's important to focus on the health and balance of the whole system, not just that final biggest power number that you can get. Also remember, I'm not a professional. I'm just a guy who's having a lot of fun figuring it out as I go, and I'm trying to share my learning journey. Just what's next for me, right now, the diversion load is the bottleneck in my whole system. And my whole show is limited by that maximum input current of 10 amps DC. And due to that limit, I can only make 1,200 watts. So with a 10 amp limit, we know that the MPPT can sweep down to 120 volts whenever it wants, and we can't control that. So 10 amps at 120 volts be 1,200 watts. So 1 kilowatt gives me a bit of breathing room. That's my I can sleep at night number. But I mean, let's be honest, I say I don't chase that final biggest number, but who doesn't want to see what all of their hard work can really do? So spoiler alert, I actually have a new diversion load coming. It does all sorts of fun stuff. Um, but when I get that installed, I'll be able to take the training wheels off of this thing and ride it to the moon. And I can do that because I feel like I understand how it all works together, how to do it safely, and then I can find that biggest number with a happy, healthy hydro system. Because as far as I'm concerned, the honeymoon phase of hydro is going to be super fun no matter what happens. But by the time you're like ready to move in together, any surprises or red flags you want out of the way, and you want to move in with a happy, healthy, stable relationship with your hydro system. It is so, so, so nice.